Although it doesn't matter in the ultimate outcome of ozonolysis, the first step of the reaction is actually going to be stereospecific, the formation of that original malozonide. If we think about why that is, it's going to be because this first step is concerted. And so two bonds are going to be forming to the two terminal oxygens at the same time. Let's show the mechanism of this and then show what product will result if this happens. So the pi electrons will attack this oxygen. These electrons will move over to the central oxygen, while at the same time, this one comes in and attacks to form the second bond. So once again, in this concerted 6-electron cyclic transition state, both bonds are forming at the same time. We can do the same thing over here to show that regardless of whether we use the E or the Z, this will happen. Now let's draw the product of the E, and what I'm going to do is I'm going to keep the bottom part of the chain in the plane of the board. So let me make sure we count the carbons right. So it's going to look like this. We're going to have an ethyl group that has been pushed down. So we're going to assume here that the oxygens are adding to the top. That ethyl group will get pushed down. The methyl group at this carbon will also get pushed down. The bond to the oxygens will form on top. Why is that? That's just by convention. We've said that the electrophile, the ozone, is going to add from the top. Half the time, it would also add from the back. So spoiler alert, we're getting a racemic mixture here. We can draw in the other two oxygens, though, and that oxygen here has formed also on the top face. So the ozonide has formed exclusively on the top. The other product we're going to get is the enantiomer in a 50-50 ratio. Now let's see what happens over here. Instead of keeping the methyl, right, notice we put this methyl group in the plane as we went down. We're going to put the ethyl group in the plane of the board here as we draw this product. So it'll look like this. In this case, we're going to get both methyl groups pushed down. Why is that? Because we can't rotate around that single bond before both bonds are formed. That's why this reaction is stereospecific. We'll still have this ozonide forming on the top. It too will form half the time on the bottom. But by drawing both of these, and then we should note that we will get the enantiomer, by drawing both of these with the ozone having added on the top, what it allows us to see is that the configuration at this carbon and this carbon is the same. So bold wedge to oxygen, dashed bond to methyl. Those are the same. The configuration at the other carbons are different. And so we have produced two different diastereomers. That's exactly what you would expect for a stereospecific reaction, where an E alkene undergoes a concerted reaction to make one diastereomer. The Z alkene undergoes the same reaction to produce a different diastereomer. Had we drawn these two enantiomers, they would also be diastereomers of each other. And not to confuse this, but this enantiomer would be a diastereomer of this. This enantiomer would be a diastereomer of this. And of course, this and these are what are enantiomers of each other.